Hello, everyone. Thank you for coming today for Molecular Connectivity Online Series, or MCOS. My name is Xindi from New Jersey Institute of Technology. In case you are new here, the Molecular Connectivity Working Group is a group of researchers that aim to advance molecular imaging as a tool to studying brain connectivity. We organize this online series as a platform to exchange ideas and promote scientific research on molecular connectivity. You can go to our website and follow us from newsletters, Twitter, and LinkedIn. Today, I'm happy to introduce Dr. S.Eickhoff. He is the full professor and chair of the Institute for System Neuroscience at the Heinrich University in Düsseldorf, and the director of the Institute of Neuroscience and Medicine at the Julich Research Center. Working at the interface between neuroanatomy, data science, and brain medicine, his aims to obtain a more detailed characterizations of the organizations of human brain and its inter-individual variability in order to better understand its change in advanced age, as well as neurological and psychiatric disorders. In today's talk, he will talk about great expectations but a bumpy road, caveats in neuroimaging analysis and modeling. I would like to also introduce Dr. Christian Habet from Columbia University in the city of New York. Today, he will moderating the discussion session afterwards. Once again, thanks for coming, and let's welcome Dr. Eickhoff.
Thank you for the introduction, and I really appreciate everybody from the US trying to, or struggling with Heinrich Heine. That's really as much of a German name as you can get. So, yeah, welcome. And over the next 40 minutes, 30 minutes, I will give you a little bit of a bumpy ride, as is in the title, on neuroimaging, machine learning, and big data analysis. These are obviously topics that we as a field and most of us are quite interested in, and certainly we can't get away from. So the basis is quite easy. We are all different from each other, be it gender, age, obviously genetics, experience, health, lifestyle. There's a lot of inter-individual variability. And in the same way, no matter what aspect of the brain we are looking at, be it structure, function, connectivity, be it with PET, MRI, whatever, we always see a marked inter-individual variability. And last but not least, we also differ quite a bit in the phenotypical output of the brain, namely cognitive performance, socioaffective function, psychopathology, and so on. So really the question is, how do these things interact? How do they play together? Can we actually predict what is going on and hence build models that explain inter-individual variability? Now, when we look at classical statistics, and which is basically the entire biomarker field, we are actually quite severely limited in terms of the model, so to speak, that we have. Why is that? Because classical biomarkers always pertain to within sample comparisons or associations. So you have your particular group of patients that you just happen to be scanned, and that particular group of controls. And really all that your statistical analysis is doing is asking, is there a surprising difference between the mean of these groups that you wouldn't expect if they're actually the same? And nevertheless, this has a long and strong tradition in biomedical research. And I guess most of us have plotted, and all of us have seen graphs like this before. So you have patients and controls. There's a highly significant difference. And if you look at the standard error bars, that all looks good. So we do have a biomarker, question mark. Well, the entire foundation of this idea of biomarkers gets shaken quite dramatically if I show you the very same data. It's exactly the same data, just in a more honest fashion. So basically, even a very strong and apparently robust group difference can mean nothing in terms of individuals. However, when we want to build models of brain variability, they are only worth, in my view, anything if they actually work on new subject. A model for those that you already know is not really a model that has any broader use. So we need to have this change in perspective, which is fundamentally the difference between classical hypothesis testing statistics and machine learning, where we go away from describing the data that we have towards building a model from the data that then actually generalizes to new yet unseen observations, i.e. a test group that was not used to build the model. And if a model like this does generalize, we have learned not necessarily something mechanistic. In fact, most of the time, not something mechanistic, but we've learned something that is robustly generalizing, that allows inference on new individuals. And it feels like the time is just right to do this. We have everything we need. We have large to extremely large cohorts. We have a lot of a priori knowledge on the brain. We have, and something not to forget, all the tools we need to handle such data, from data management to high throughput computing. So full steam ahead, isn't it? Well, it definitely looks like it. And I give you a old and tested, but I think very instructive example on modeling inter-individual variability, which is age. We know that we all age. And if you look at the brain on the left, that's a 20-year-old subject, and the one on the right, which is somebody in their late 60s, we can see it by eye. Now, we also know, though, that not everybody ages in the same way. And here I want to refer back to the idea of using machine learning to build neurobiological models. So we know people age, we know they age differently, but we can certainly postulate that there should be something like canonical age trajectories. So we can actually frame that in a predictive way by saying, can we build a model that correctly predicts the age of a new subject only from seeing the brain? This kind of idea, brain age, is certainly not new, but I really like to use it as an example for model building, because if such brain age prediction does work, it does not only have a practical or potentially practical application in learning something about a new individual, but it also, and in my view critically, demonstrates that the model has actually learned something like this canonical aging trajectory. And it does so very well. So this is a figure from our own work, but we know that there are many papers now that basically show that in a general population setting across the lifespan, you can predict the individual age with a mean average error of about 4 years. So in spite of all the variability that people show, we can actually predict, model these kind of canonical trajectories, and we can moreover show that deviations from these canonical trajectories, they are associated with many neurological and psychiatric disorders, as well as general health, lifestyle, cognition, and so on. Now, in some way, this is almost trivial, because as you have seen on the slides 2 back, we can do this. I mean, we see when the brain is old. Now let's take another example. Again, this was the old versus young, but what's the difference between these brains now? The two brains here in the middle. You see that you don't see anything, right? They basically look identical. Yeah, indeed. It's a male and a female brain, and we actually had the fun once to do a little informal test with some of the neuroradiologists we know at the various university hospitals around us, and even somebody who has seen 10,000s of MRIs in their life. They are at chance level. You can't tell male and female brains apart as a person. Now, what does the computer say towards this? Oh yeah, it's a fairly easy task. So basically, what this demonstrates is that on the one hand, we can use this kind of machine learning models to actually learn something like these canonical trajectories, but they go beyond that and can actually pick up distributed patterns that we as humans cannot see. And the reason we can't see them is because they're distributed. So even if we get shown what kind of features contribute, it seems like we are lacking the high dimensional memory or imagination to put things together at various places of the brain. So this is all good. And then obviously the next extension is then to not only predict in inverted commas, something that is already there, but to predict in the real sense something that will happen. For example, predicting the success or failure of interventions. It's a study we did with Tim Peppel in Aachen at that time. He's now in Regensburg, trying TMS for new tinnitus therapy. And it worked somewhat. So it worked in roughly a third of the patients. And they took MRIs prior to the intervention, and we tried to see whether we can actually use machine learning on these MRIs to actually predict who will benefit from the intervention. And in the end, we got to an accuracy of about 85%. So indeed, there is, again, something in the brain, not only that we can't see, but also something in the brain that we can't see that tells us something about the future. Coupled with the fact that we can also in large cohorts predict individual phenotypes quite well, it seems that overall we're in for a very bright future. And this is really, I would say, the state of the field. Not sure nowadays anymore, but certainly was the state of the field a few years back. It could only get greater and greater. So let me spoil the party a little bit and also show the more cloudy aspects of neuroimaging and machine learning that we come to, in some way like, because they, in my view, hold the key to actually make these things useful. In order to do so, let's walk down the machine learning pathway. You start out with some data. That's the thing you want to predict from. And that's, for example, an MRI. And you have a target. That's the thing that you want to predict. Now, before you can actually do the prediction, you have to convert the raw data that you have into some form of features. And before somebody says, well, not with deep learning and convolutional neural networks, okay, so some people say like, well, with deep learning, you don't need this kind of feature extraction because we have this nice end-to-end pipelines. Ultimately, the more or less explicit feature creation is just replaced by the architecture choices. It's in the end the same thing, how you define so it's not feature engineering, it's architecture engineering. But in the end, you always have the same thing that you're not doing the actual prediction on the raw data, but rather on some form of features derived from it. Then you have the prediction model, obviously, and I'm not going to talk a lot today. In fact, basically not at all about the different prediction models that are out there, which is a talk on its own. Once you build the model, you need to validate it, and then finally you have a product that you're ready to employ. Okay, that's the general overview. Let's dive a little bit into the individual steps. And it starts already with the data. In fact, the question, what, if anything, is actually my data? So here, Georgios Antonopoulos did an interesting study with T1 MRI of about 2,000 subjects, broad age span from different centers. And what he did is to run 10 standard pre-processing pipelines. And if you look at what's in there, this is like the absolute standard stuff. ANTS, FSL, CUT, the different template segmentations. If we would make a survey here, people would use any of these. And really, if we're honest, you're using what everybody else in the lab is using. If you're a young person, or you're using what you've always used if you're an older person. But nobody, I think, would argue that any of these is per se right or wrong. They are like these standard tools. Now, what happens if we run this on every pipeline on all of these subjects, and then per brain region, see how well the different results correlate? Oops. What we see is that basically, if you correlate the volumes pairwise between pipelines and then average that, you basically see that on average, we have a correlation between the values yielded by the different pipelines of around 0.5. So at best, there's a low to moderate agreement between the pre-processing workflows. And in some areas, for example, here in the posterior parietal cortex or in the middle frontal lobe, it gets even worse. So basically, all standard pipelines, but the correlation between the outputs of these pipelines are at best in moderate agreement. Now, what's interesting is he then also showed if you feed that into prediction models, the predictions actually are quite similar in their performance. But it becomes a solid problem if you want to walk back to the actual raw numbers underlying that. Well, I basically almost skipped the step because I said per region. And per region is important in neuroimaging because what we get out of the scanner is something like a few 10,000s, a few 100,000 voxels. And as a rough guideline in machine learning, you should definitely have more observations, more subjects, than you have features. Now, if you have 200,000 voxels in a VBM analysis, you're going to have to scan a lot of subjects to actually have more observations and features. Well, luckily, the brain is topographically organized. So rather than looking at the individual voxels, we can get away quite nicely by using something like an atlas-based compression. So we take a brain atlas and then just run the analysis, the predictions, on one value per atlas region. Yeah, but which atlas? Because unfortunately, there are many different brain atlases. Does it matter? Well, you can almost guess the answer, right? This work by Justin Domov, this time on resting state connectivity, basically looking at some of the standard graph theoretical measures, obviously for the same data, just calculated on different atlases. And without going too much into the details, you kind of nicely see that whatever you get out is basically whatever you choose to put your data through. So from that point, we are already starting to be on somewhat shaky ground because on the, let's say, conceptual side, we start with our data that we want to predict from, but the data that we want to predict from is everything and nothing. We have to put it through processing pipelines, and we have it through put it through some sort of a representation to get our features. And I really would like to stress that point that this, in my view, is the most overlooked, if not ignored, part not only of neuroimaging and machine learning, but all of neuroimaging. What do we actually do to the data before we run the statistics has massive influences, and there are in some way too many good options. It would be nice if there's one right pipeline and everything else is wrong. It would also make our lives as reviewers a lot easier. The problem is none of the pipeline, none of these atlases is per se wrong, but still, they all give you different results. Just to show you how strong the whole effect is, this is actually on personality prediction from diffusion-weighted imaging. So I'm jumping a bit. And what Amelie Rauland here did is an amazing feat of work. She ran 123,000 pipelines on the data. Same data, same subjects, just more than 100,000 different pipelines predicting personality from diffusion data, which I think is not a bad idea. So what you see is that overall, and it's a histogram of the different pipelines, you get nothing. You can't predict it. But if you choose to focus, you can actually get predictions up to almost 0.3 with the right pipeline. And I always wonder a bit how to frame or phrase this part of the talk. Let's put it this way. We don't know whether these are the only correct pipelines because they only reveal what is truly going on and the other ones get a lot of noise, or whether they are dangerous lures that may trick people into believing that these are the best pipelines and publishing this result here, ignoring this part here. We don't know, but I feel that if you look at the current state of the field, and if you look at the current state of the literature, we definitely see more of these than we see of these. Whereas the actual raw numbers are not quite in favor of the strong results. Yeah, so we can't predict personality from DWI. That's a bit disappointing. And it actually brings me, oops. And in fact, it was very disappointing when we discussed it. So we recommended Amelie to run a control analysis, this time not on personality, but on cognitive variables. She didn't do it for the whole set of pipelines, but just for a subset. And what did we see? In fact, there was a marked shift. So whereas for the personality prediction, you ended up with give or take nothing, there was a very robust, very strong effect on the prediction of cognitive scores, which brings us to the aspect of how much is your prediction accuracy actually dependent on the targets. And here I really have to laudate Martin Gell for his work, who started with a very simple experiment. He took a easy, well-established prediction, such as age, and then running the same pipeline, same subjects, same processing, but artificially degraded the reliability of the target variables. And what do we see? Prediction accuracy drops substantially. And in fact, we can empirically validate that if we look at the different measures from the UK Biobank for which test-retest reliability scores are present, or do the same in ABCD, we always see that there's a positive correlation between test-retest reliability of the scores and the prediction accuracy in predicting them. Now, what does that mean effectively? It means that we, of course, have this kind of saturation curve for predictive analysis. If you add more and more subjects, your predictions get better and better, but after a strong increase after the first few thousand, it really tails off. So going from 200 to 1,000, big jump, 2,000 less, 3,000 less, 4,000 less. We have other studies where we did this up to 40,000. You start off to go asymptotically. But this only holds if you have a good reliability. If the reliability is poor, nothing can save you. If you have a target that is poorly reliable, and I'm quite glad I don't see the faces of all the clinicians and personality researchers now. If you have a poorly reliable target, you can have any sample size you want. You don't get a good prediction. Coming to the model and some of the other hiccups that we observed, now it gets frightening. I already talked about these asymptotic saturation curves. Here, Omid Warner actually did this up to 20,000 subjects. And he was an electrical engineer coming from signal processing. And many of you probably know there's tons of things you can now do to torture resting state fMRI time series. Like there's the standard connectivity, and there's entropy, and there's transfer this, and there's like it gets really freaky. And he was interested in that, and he tried all of that. And basically, what you see is, yes, there's a certain ranking of the different classical, modern, and hyper crazy stuff you can extract from resting state fMRI. And they all kind of tail off after about 10,000 subjects. So far, so good. And then we did this control analysis, just predicting the target variable from age, sex, and intracranial volume. And it was a lot better than any, even the most sophisticated methods. Even with a small number of subjects, just using age, sex, and intracranial volume, you substantially outperformed even the most sophisticated analyses on 20,000 subjects. Why is that? Well, because effectively, machine learning models are not only tools for lazy people, but they are also extremely lazy, and they really, really like shortcuts. Let's go back to the other study that I showed you on the gender prediction. Again, nice performance, but if we look into detail, what we actually see is basically all the algorithm used was head size. If it's a small head, then it's more likely a female person. If it's a large head, it's more likely a male person. And you see that quite nicely by the misclassified examples. All the women who are rather large, tall, or most of them were misclassified as male, and the males like me, like 5'9", they are more likely to be classified as female. It's all just about size. Now, what happens if we, as good scientists do, explicitly regress out a confound? If you regress out head size, yep, then we don't have that confound anymore. But unfortunately, we also don't really have a good prediction anymore. So in the end, what we need to overcome this problem of models being really, really keen to identify and exploit shortcuts is to A, recognize the danger of these shortcuts, B, identify them, and C, very explicitly design the pipelines such that they are unaffected by confounds that we are and or can be aware of. But this brings us on the more philosophical or conceptual point to an absolute conundrum, an absolute rabbit hole, an absolute hell, which is that human variability is likely very low dimensional. So if you look, for example, at the UK Biobank, there are like 10,000 of variables per subject. But it should be quite clear that we don't differ from each other in 10,000 independent aspects, but rather, and we've tried that, I don't have the figure here, rather there's a very strong intercorrelation of basically everything. And if we approach that, as Vera Kohlmeier here did in the preprint that you can find on medRxiv, from the more conceptual level, we really end up with more of a gradient of confounds. So everybody, including myself, who has always been taught that there's a binary thing, there's a variable of interest, and there's a confound, a variable of no interest. I'm sorry, that's not true in the big data domain. Now everything and nothing can or is a confound because it's really a gradual shift. I mean, some things are very avoidable. Like if your patients are on average 10 years older than your controls, yeah, that's kind of trivial. Then it gets more interesting with these, and we find more and more of these implausible but potentially very critical biological links. So there is a GWAS hit, and there are MRI findings for the biobank item, how often do you eat bacon for breakfast? Okay, what's the neurobiology of eating bacon for breakfast? Well, one point of view is the sort of, I try to save neurobiology, or maybe it has to do with saline receptors on your tongue and potentially you like bacon more or less. There's the more skeptical point of view, which is like, well, there's a large proportion of the, or substantial proportion of the British population made up of immigrants, mainly from Pakistan and the Near East, that just doesn't eat bacon. So in the end, bacon here may just be a proxy for ethnicity. And then there are aspects that can be seen as reflections of latent dimensions. One, like the big example here is for example, again, ethnicity, gender, socioeconomic status. These are things that kind of correlate with everything, to be honest, without, at least for socioeconomic status and ethnicity, we have any good or plausible biological links. Particularly for gender, there are quite a few things where we can at least assume that there's a certain identifiable common factor, like hormones. And last but not least, but again, the endpoints of a gradient are always trivial. They're basically measured. You have two variables that are measurement of give or take the same thing. So the endpoints we kind of can forget about, but here things become really messy. And in fact, for every single study that we do, we notice that. Can we actually assume that this is true? Or can it again be a shortcut, a reflection of some confounding aspect? And why would that matter? Because I talk a lot to clinicians and they say, yeah, so what? As long as the algorithm predicts well, I don't care what it predicts on. Well, this is true as long as you apply the algorithm exactly to the same population that you trained it on. So Jingwei Li tried this explicitly using the HCP and the PNC data, basically training models on the overall population, training models on the white American subgroup, and then seeing how do the models perform on the African American subgroup. And to make it short, it didn't even fail gracefully. It basically did all sorts of stuff. There were times when the prediction accuracy was just bad. At times it had an offset bias. At times it had a slope bias. At times we had slope and offset. Or it was slope, offset, and just being poor. So the key thing here is, if your algorithm exploits any shortcut through confounding, that is okay as long as the relationship between your confounding factor and your target is exactly the same in the training and in the test population. However, we can almost be guaranteed that whenever you move outside of a super narrowly defined population, you will encounter things like confound shift or confound drift, which in a nutshell is exactly what we see here. Models that are trained on population A and exploit a shortcut in population A. If you apply them to population B, they do all kinds of things other than just working well. Just further examples of that. So this brings us to a rather critical issue when it comes to actually thinking about application, thinking about real life relevance. Because here we obviously face issues of acceptance and responsibility. Both of them are very closely intertwined with the question of explainability. And the best way to frame this explainability is show me the evidence, or as the old lady would put it here, so why? And if you as a clinician can't answer the why, and maybe even the programmer struggles with the why, good luck convincing her in actually taking something that may be really helpful. Now, we've written quite a bit about these ethical and societal challenges. The point I just mentioned is in this human brain mapping paper on your evidence. And I want to briefly highlight this because there's one important sub-aspect, which is that from a philosophical point of view, we can only understand new information, we as humans, if it integrates with existing knowledge or experiences. And this is where a particular problem of these models lies or will lie in the future. So I'm coming to an end of the presentation. I hope that I have convinced you that only machine learning allows to build generalizable and test generalizable models of brain organization and hence individual prediction. But the performance of these often very complex workflows can be shockingly brittle, and conceptual and biological challenges meet ethical, legal, and societal ones. With that, I would like to close by thanking everybody from our institute and the funders, and obviously you for your attention. And I'm very happy to take questions. Thanks.
Yeah, thank you very much. I thought that was a very stimulating talk. I think it's very timely, and it's funny the one anecdote that comes to my mind for all the Germans here when Simon said about the model taking shortcuts. It always reminds me of der kluge Hans. I don't know, clever hands also.
It's actually called the clever hands phenomenon in machine learning. Yeah.
Yeah. So clever hands. Look it up. It's a really funny anecdote, but yeah. So I think I like if people could just unmute themselves and speak. That's usually better than me reading from the chat. So just fire away. Maybe briefly say who you are. That would be great. Wow, that's overwhelming.
Hello.
Yep.
Hi, Simon and Christian. Hi, thanks for moderating this. Simon, thanks for the great talk. I've always been perplexed with the amount of and the volume of work you guys do. So it illuminates a bunch of us all around the globe, I'm sure. I'm currently a postdoc at Albert Einstein College of Medicine, New York. So I had some, I guess, simple questions for you. So when you showed that personality can be predicted so easily, which I guess is a higher dimension than cognitive aspects, do you have, what's your take on which particular cognitive cognitive aspects can be predicted better as compared to others? Are
Yeah.
there some which are predisposed to be predicted little better than others? If so, then why?
Yeah. So I think there are several aspects that come into play, and that's not only from this work, but actually quite a few different studies that we've done over the years. The way we informally framed it is hard versus soft targets. I try to formalize that a bit by saying that hard targets are things that you can measure and hence have also a defined and usually quite good test, retest reliability. So you really have a rather direct reflection in your target numbers of what you want to actually predict. Very simple example, working memory. Like if you test the digit span, this is exactly how many numbers you can in parallel hold in your head, right? This is the digit span you measure is exactly the digit span you can offer in your brain. And if you repeat the analysis, it's quite the same. Similar to other things like trail making tests and most of these rather simple cognitive tests, the construct that you want to measure and the measurement are closely related. The measurement is objective and the measurement is reliable. Now, the entire other end of the spectrum is, in fact, personality. We don't even know what we exactly want to measure because we have a, let's say, human notion of what personality is. And just starting to put that into numbers, if you, well, I happen to teach personality also at the graduate school level. So, I mean, it's bizarre if you look at the number of models that are out there for personality. And they kind of agree in many aspects, but disagree in even more. So in contrast to numerical working memory versus digit span, the ecological or validity jump from personality to personality score is already a big one. But then on top of that, digit span, you can just probe as is. You give the subject digits. Personality, even if you would agree on factors, even if these would be the hypothetical correct factors, you still would need to measure them by questionnaires with all the noise that comes in through the different effects, self-serving bias, Southron effect, and so on and so on and so on, right? So I like to use digit span and personality traits really as the opposing ends of the scale between the thing in your brain, the thing that the construct, and the measurement. In one case, it's all very tight. In the other hand, well, that's why we call them the soft targets. Every step needs a solid leap of faith. And what we see really persistently through by now hundreds of analyses is that the harder the target, the better the prediction. And Martin and Amelie in their work framed it sort of a bit more simplistically as reliability, but I think it actually goes beyond reliability also on this connection between what is in the brain and what is the construct we're trying to measure.
Thank you.
Okay, Igor, next.
Simon, do you hear me?
Yeah.
Thank you. Very inspiring and provocative talk. I like such talks very much. And I have also a sort of provocative question. So on one hand, we have biological variability, individual variability. On the other hand, we have methodological variability, right? And methodological variability, if it's large, and it seems to be large currently, may not allow us to capture at least certain biological variability. would you say that the field should go in limitation of this methodological variability, risking that some biological targets cannot be captured, or the field should, as it now goes, it's my impression at least, into expanding methodological tools and methodological variability, and maybe due to this high variability, there is a risk that relevant biological targets or biological variability cannot be captured?
Several answers to that. First of all, I think the field is moving in the right direction, but let's move carefully not to break public trust. I'm not saying deliberately, I'm saying let's move slow, but we have a big danger of eroding public trust if we shoot out preliminary things that later don't really turn into actual benefits. And in my view, this has happened in the imaging field since at least the 80s. I mean, it's not the first time. We've seen so many waves of now we solve all the issues, we heal all diseases, and in the end, people fell somewhat short of the expectations, put it this way. Now, in our particular field here, I think, or where I'm really am a big fan of, or what I'm a big fan of, is this kind of multiverse analysis. So you basically, I mean, you don't have to do the full Amelie and run 120,000 pipelines. But this is something where you really get the full picture, and maybe also just what I showed here. If you look at the personality versus cognition, and this is a multiverse analysis that's not so big to do. I mean, this was, I don't know, a few days of compute. You really see that you can probably have a solid amount of trust in the cognition prediction, maybe not in the absolute number 0.29 or whatever as the accuracy, but you certainly see, yes, there is something that is really solidly predictable, whereas you don't have the trust on the personality side. And I really feel that these kind of multiverse analysis, which are not that expensive nowadays anymore in terms of compute, can really help to A, install trust, and B, also calm down the field. I mean, we do have a big problem if R equals 0.35 is published, because then everybody else coming afterwards is like, oh, it has already been shown that you can do it. So why doesn't it work on my data? Right? This is a huge problem. So yes, it kind of takes off the bus a bit, but I would argue it's a good thing that it takes off the bus a little bit, provides a more honest representation, but then again, if you see something like this, is a very good trust building exercise, in particular, if our midterm perspective is to actually come up with something, to develop something that is useful and used.
Thank
I saw
you.
another question in the chat about denoising in a cohort. We want to identify a network related to the, it was an essential tremor, a network related to the tremor, but without motion. Well, let me just, I'm not so good today in flipping through the slides here because somehow my computer is a bit slow, and if I'm pressing escape twice, I'm gone again. This is basically something for that slide. In the end, if you're too far down the road here, nothing can save you. If the thing you want to analyze is too highly correlated with your confound. Worst case, if what you want to analyze is perfectly correlated with the confound. There is no way you can separate them. That's the bad news. The somewhat good news is if you are somewhere here, although I think you're quite far down the list with essential tremor and the tremor network, the best I could offer is to keep the analyses rather separated. So if you want to remove motion artifacts, basically do it in a model that's, for example, trained on the entire data, patients and controls, and remove it as blindly as possible. Definitely consider this preprocessing part of your modeling pipeline and only estimate preprocessing parameters in your training group. This is one of the most common mistakes. Now, I rarely use the word mistake because I think it's a bit harsh, but if you do a joint preprocessing and denoising with training and test set, if you fit one model for motion regression on your entire data to remove data, including the test subjects, then you will have leakage and you will be overly optimistic. So you can fit a model on for motion regression on, but then do it only on the training data. And I would strongly advise to also explicitly test how well does that model actually remove motion noise in the test data, or do we still have it in there? But in the end, this is all on rather thin ice anyways. If you have something that is intrinsically strongly linked to your feature of or your target of interest, then the closer it's linked, the less your chances are that you can actually separate it. And let me give another caveat, if I may. It's not that this is something where size only helps. If you have a larger sample size, these smaller residual effects can still decontaminate your data and affect quite a bit. If you have a large training group and you really removed motion quite well, but if you're a very large group, then still that bit of motion that's in there in a large group can still be leveraged. Conversely, if you have a very small group, you almost certainly get some false positives where motion interferes. Now, what can you do? Again, not too much, but things like split or subsampling analysis can help. But overall, we, I think, must acknowledge the limitations. If a confound is too strong, we basically are always stuck with it. Sorry for the negative answer.
Igor, one last.
If there are other questions, I can wait.
No, go ahead. Go ahead.
Just a follow-up question, Simon. So you showed this plot, with 0.35, a finding with a, let's say, more or less accurate prediction, which in fact can be published, while all other very low prediction accuracy will not appear in the literature. And so what do you think if, yes, unfortunately, so, but can this be changed? So should the community put efforts into promoting publishing of negative results?
Well, odd chance. You hear me on a rather positive note. I think it has already become a lot better. If I think back, let's say 15 plus years, when the sample sizes were smaller and you could play around a lot more with things. I mean, I've known students that played for half a year with their data until they finally found the amygdala in the right contrast, because the supervisor clearly said them, if you don't find the amygdala, we can't publish it. So they spend a lot of time and effort redesigning their GLM and their outliers, their pre-processing and everything else around it until they found the amygdala. So I think actually as a field, we've moved a very long way. Publishing null results has become acceptable. It's still, and I'm not being overly optimistic here, it's still harder than publish positive results, a lot harder. But I feel we are on the right track. And I hope, and I'm not sure we can actually top down in any way, apart from the question of who would be top down. But I don't think we can enforce it in any direction. And in fact, you may be surprised to hear that, but I'm not so big a fan of pre-registration. I mean, if you pre-register it, then let's say your pre-registered pipeline is that one here. Or let's say that one here, somewhere one of these. I mean, here's a couple hundred pipelines, probably a couple thousand pipelines that perform at 0.12. You pre-register it and you get a 0.12. What have we learned? We have certainly learned less than, again, I'm trying to promote something here, than from such kind of multiverse analysis where we see what kind of an impact different pipelines have. So no, pre-registration probably is not the answer to that. Unless you have a clear yes-no hypothesis and a simple pipeline. It works well in cognitive psychology if you do reaction time. Like, is reaction time faster or longer under condition A or B? This is something you can pre-register well. These kind of things, I don't think so.
Alrighty. I think this is maybe a good way to stop. I certainly, by the way, I think this is the multiverse idea, and this idea that, you know, pipelines should be part of the modeling step. I think it's a real sea change that's really important. You know, particularly pipelines, you know, each stage in a pipeline sometimes encompasses whole careers for individuals, right? People work on slice timing. What's the best way to do that? You know, or, you know, motion correction. So there is, and, you know, the work of Steven Strother, for instance, looked at pipeline dependence, but there's still the idea, oh, there is one absolute best pipeline that everybody should be using, and that's just I think that's probably untenable.
I fully
right?
agree. I don't think there's anything like that.
Yeah. So highlighting the dependence, I think, is really crucial. I would just hope if you know, this postdoc of yours or student of yours who did this amazing labor of love, I don't know how, it must have been awful to do 100,000 plus pipelines. You know, at some point I would
not by hand.
not by hand, but at some point it would be great to, if there are consistencies where some pipelines, you know, consistently for several endpoints.
Look, I mean, the paper's out. We looked at that, and
okay, not really. Okay,
unfortunately.
Right. Okay, we'll leave it at the postmodern deconstruction. Yep. Okay, so if nobody else has any, do you want to say something, Shin? You should have the last word. You're the real boss here.
No, thank you very much. It's really a wonderful talk. Yes, I do. I think in neuroimaging, like 10 years or 15 years ago, we have this double dipping or, you know, voodoo correlation thing. And so I think we have a kind of aware of those kind of choice, like hyperparameters, whether you choose that one, that you selectively reporting things. But I feel that I talk to a lot of like computer science. They are not aware of this. They are just trying different architecture, as you said, like architecture, engineering, this like that. But
they are often really in a innocent to positive way. Think they are just trying things and don't mean it bad. Like, in particular, if you look at students, like, well, I'm so curious. I want to find the best pipeline, and then you do obviously you test a lot of pipelines, and it's called the I tried a few things phenomenon.
Right.
Always get overly optimistic if you tried a few things.
Yeah. And also like in very old like psychology, they have said like if you torture data enough, they will confess. Like same kind of energy. Yeah. But I think we have the same question that maybe we need to make it aware, like especially for this big data, and then there are a lot of other fields like engineering. I think those people may have less aware of that. Really, thank you very much for Simon for the wonderful talk. I think if we do not have any other questions, then we can stop here. I really thank everyone to come. Really, hi, thank you. Yeah,
Bye.
thank you.
Thank you.
Bye.
Thank you. Bye-bye.